live in a world that exhibits extraordinary levels of order and organization on all levels, from the smallest molecules to human social organization to the entire universe. And we might say that it's the job of the enterprise of science to try and understand this extraordinary order and organization that we see in the world around us. And in many ways, we've been very successful in the past few hundred years in making progress in this project. We understand the workings of the atom, the structure of DNA, we understand the origins of the universe, how galaxies form, and the precise elliptical orbit of the Earth around the Sun. But what all these systems that we've been so good at describing and predicting have in common is that they are inert. What I mean by this is that they do not have any degree of autonomous adaptive capacity. Here we can make a fundamental distinction between those systems that are composed of inert elements and those that are composed of adaptive elements. Because these inert systems that are studied in physics and chemistry do not have adaptive capacity, we can describe them through a single global rule. We can write equations about how chemical elements will react when combined, or how the solar system will change over time according to a set of differential equations in a deterministic fashion. Unfortunately though, this approach does not work when dealing with systems that are composed of adaptive elements that are non-deterministic in their behavior. Adaptation gives the elements in the system the capacity to respond in different ways depending on the local information they receive, and the overall organization that forms is in fact not a product of a global rule like we might have for a chemical reaction, but instead is a product of how these adaptive agents respond to each other. With these adaptive systems, the overall makeup of the organization is not necessarily defined by a top-down rule, but may emerge out of how the elements adapt and respond to each other locally. There is no algebraic or differential equation to describe how international politics works, why families fall apart, or the success of a business in a market. The overall workings of these adaptive systems is an emergent phenomena of the local rules and interdependencies. It is these systems composed of adaptive agents that are interdependent that game theory tries to understand and model. A game is a system wherein adaptive agents are interdependent in affecting each other and the overall outcome. Game theory is the mathematical modeling of such systems. These adaptive systems are pervasive in our world, from cities and traffic to economies, financial markets, social networks, ecosystems, politics and business. The central ingredients of these systems is that of agents and interdependence. Without either of these elements, we do not have a game. If the elements did not have agency and the capacity for adaptation, they would have no choices, and we would have a deterministic system. Likewise, if they were not interdependent, then they would not form some combined organization, and we would then study them in isolation, in which case likewise we would not have a game. Games are formed out of the interdependencies between adaptive agents. So what is an adaptive agent? An agent is any entity that has what we call agency. Agency is the capacity to make choices based upon information and act upon those choices autonomously to affect the state of their environment. Examples of agents include social agents such as individual human beings, businesses, governments, etc. They may be biological agents such as bacteria, plants or animals. They may also be technologies such as robots or algorithms of various kind. All of these adaptive systems regulate some process, and they are designed to maintain and develop their structure and functioning. For example, plants process light and other nutrients, and their adaptive capacity enables them to alter their state so as to intercept more of these resources. The same is true for bacteria and animals. The same is true for a basketball team or a business. They all have some conception of value that represents whatever is the resource that they require, whether this is sunlight, fuel, food, money, etc. This creates what we can call a value system. That is to say, whatever structure or process they're trying to develop forms the basis for their conception of value, and they use their agency to act and make choices in the world to improve their status with respect to whatever it is they value. As we can see, this conception of value is highly abstract, and as we'll discuss in a future module, this value system can be very simple or very complex, but it forms the foundations to what we're dealing with when talking about adaptive agents and games. You can't model a game without understanding what the agents value, and the better you understand what they really value and incorporate that into the model, the better the model will be. Thus, agents can also be defined by what we call goal-orientated behavior. They have some model as to what they value, and they take actions to affect their environment in order to achieve more of whatever is defined as value. In game theory, a game is any context within which adaptive agents interact and in so doing become interdependent. Interdependence means that the values associated with some property of one element becomes correlated with those of another. In this context, it means that the goal attainment of one agent becomes correlated with that of others. The value or payoff to one agent in the interaction becomes associated with that of the others, and this gives us what we call a game, wherein agents have a value system. They can make choices and take actions that affect others, and the outcome to those interactions will have a certain payoff for all the agents involved. A game then, being a very abstract model, can be applied to many circumstances of interest to researchers, and it has become a mainstream tool within the social sciences of economics, political science and sociology, but also in biology and computer science. The trade negotiations between two nations can be modeled as a game. The interaction of businesses within a market is a type of game. The different strategies adopted by creatures in an ecosystem can be seen as a game. The interaction between a seller and a buyer as they haggle over the price of an item is a form of game. The provision of public goods and the formation of organizations can be seen as games. Likewise, the routing of internet traffic and the interaction between financial algorithms are also games. To quickly take a simple, concrete example of a game, let's think about the current situation with respect to international politics and climate change. In this game, we have all of the world's countries, and all countries will benefit from a stable climate. But it requires them to cooperate and all pay the price of reducing emissions in order to achieve this. Although this cooperative outcome would be best for all, it is in fact in the interest of any nation state to defect on their commitments, as they would then get the benefit of others reducing their pollution without having to pay the cost of reducing their own emissions. Because in this game, it is in the private interests of each to defect, in the absence of some overall coordination mechanism, the best strategy for an agent to adopt, given only their own cost-benefit analysis, is to defect. Thus all will defect, and we will get the worst outcome for the overall system. This game is called the prisoner's dilemma, and it is the classical example given of a game because it captures, in very simplified terms, the core dynamic between cooperation and competition that is at the heart of almost all situations of interdependency between adaptive agents. In the interdependence between agents, there comes to form two different levels to the system. The macro level, where they are all combined and have to work cooperatively to achieve an overall successful outcome. And the micro level, wherein we have individual agents pursuing their own agendas according to their own cost-benefit analysis. It is precisely because the rules and dynamics that govern the whole and those that govern the parts are not aligned that we get this core constraint between cooperation and competition. This is what is called the social dilemma, and it can be stated very simply: what is rational for the individual is irrational for the whole. If you do what is rational according to the rules of the macro level, to achieve cooperation, then you'll be operating in a way that is irrational to the rules of the micro level, and vice versa. If either of these dimensions to the system was removed, then we would not have this core constraint. If the agents were not interdependent within the whole organization, then there would be no macro level dynamic, and the set of parts would be simply governed by the rules of the agents locally. Equally, if each agent always acted in the interests of the whole, without regard for their own cost-benefit analysis, then again, we could do away with the rules governing the micro level, and we would simply have one set of rules governing the whole organization, and thus there would be no core dynamic of interest. Things would be very simple and straightforward. The complexity arises out of the interaction between these two different rule sets and trying to resolve it by aligning the interests of the individual with those of the whole. So in this video, we've given an outline to what game theory is, talking about it as the study of situations of interdependence between adaptive agents, and how these interdependencies create the core dynamic of cooperation and competition that is of central interest to many. In the coming videos in this section, we'll talk about the different elements involved in games and the different types of games we might encounter.